So there's a range to it, right? Water is just, water is just fine. You can drink water. There are some solutions that are slightly acidic or slightly basic, but there are some solutions that are strongly acidic and strongly basic, the ones that can hurt you. Think of like battery acid and drain cleaner, things like that. Okay? So there's definitely a scale to it. Let's talk about what that comes from. A strongly acidic solution has a relatively high concentration of what is responsible for acidic properties. What did we call it? Hydronium. H3O plus is hydronium. It's an ion that ends in ium, which is plus. Remember, the ammonium ion was on your polyatomic ions list, also plus charge. Okay. Strongly basic solution has a relatively high concentration of what? Hydroxide, OH minus. So what do you suppose that would mean about a neutral solution? If a solution was exactly and perfectly neutral, what would we say about the amount of hydronium and hydroxide? You got it. Has equal concentration. Okay. But it turns out that as one increases, the other decreases. They're sort of opposites. But a basic solution, okay, like that one up there, that would have a high concentration of hydroxide, a basic solution still has some hydronium ions, though. Okay? They're not all gone. It's just that the concentration of hydroxide is greater than the concentration of hydronium. Okay? So when we put something in square brackets, like that, that's the molarity, or the molar concentration. Right? Moles per liter. So when we put a formula of something in square brackets, we're talking about its concentration, okay? How concentrated it is. If we were comparing the caffeine concentration in various drinks, we could say caffeine in square brackets equals so many molar or something like that. Okay? So just when we're talking about how concentrated a certain substance is, we put its formula in square brackets like that. So OH minus in square brackets means it has a higher concentration than hydronium ions. And then vice versa for acidic solutions. So it's like a balance. Okay? The more acidic it is, we have more hydronium and less hydroxide. Okay? As it becomes neutral, they become more equal. Okay? As it becomes basic, we have more hydroxide than hydronium. Okay? They have that sort of inverse relationship with each other, but the relative amounts of those two ends up determining what makes a solution acidic or basic and how acidic and basic it is. Okay? So we have a very handy 0 to 14 scale, which is used to measure and rate the acidity of a particular solution. So neutral pH is right at 7.00. Okay? And the acidic side is towards 0. Okay? We're the most acidic at this end, and the most basic down towards 14. So if you take a look at this little chart that I borrowed here, you get things like milk. Here's vinegar, pH around 3, lemon juice, battery acid. Okay? The closer to 0, the stronger the acid, the more acidic it actually is. Okay? This was sort of from an environmental source. So normal stream, here's precipitation gets a little bit more acidic. Acid rain can be caused from pollution sources that make the rain even more acidic than normal. So acid rain could be anywhere between 1 and 4, but adult fish can die when their pH approaches 3 or something like that. So on the basic side, baking soda, seawater is slightly basic. Here's milk of magnesia, an old-fashioned antacid. Right? Antacids are bases because they neutralize acids. Right? Here's ammonia. If you're doing the at-home lab, ammonia is quite basic. Lye, even more so. Okay? Lye is sodium hydroxide, okay? Or potassium hydroxide, sometimes a mixture. Okay? You notice this color scale that we tend to use fairly commonly. That's the litmus color scale. So litmus paper turns red with more acidic solutions, turns blue with more basic solutions. That's sort of a common color coding scheme that we use for acids and bases. So let's talk about, though, it's kind of an unusual scale. It's got 7 right in the middle. 0 is the more acidic end, and 14 is the more basic end. It's kind of an odd scale that comes from that way. But, also, I wanted to say 7.00 is perfectly neutral. So what would 7.5 be? Yeah, slightly, but it would be slightly basic. Okay? So keep that in mind. And this is also chemically neutral when we're talking about hydronium and hydroxide. Neutral for blood pH is somewhere within the 7s there. So you could technically be too acidic for your blood, but, I mean, for instance, 7.0 would be way too acidic for your blood. Okay? So I don't want anybody dying thinking because they learned that 7.00 is neutral in chemistry. That's